Hello, pre-calculus students, and welcome to our conclusion of section 2.5 on higher order polynomials and all of their complex zeros. And we conclude this lesson with the most important theorem, the fundamental theorem of algebra. And as a general basic guiding principle, anytime you see the word fundamental, that means it's important. And this is what the fundamental theorem of algebra says. A polynomial f of x with degree n has exactly, and that's nice when you can say the word exactly in a theorem, n zeros. And I should qualify that by saying n complex zeros. Some of them may be real, some of them may be complex, but there are whatever the degree is, that's how many zeros there are. Some zeros may be repeated. Okay. And this is really, really nice for us to look at in many ways, because you look at some of these problems, well, find all the zeros of this. Well, how many zeros are you supposed to find? How do you know you're done? Well, it's easy now with this theorem. The degree here is 4. There's 4 zeros. The degree here in this problem that we're about to do is 4, so there's going to be 4 zeros. Any quadratic is going to have 2 zeros. They might be complex. They might not show up on a graph at all, but there's going to be 2 of them. Okay? So we're going to finish this with kind of one big example here where we're asked to find all of the zeros of this function. G of x equals x to the 4th plus x to the 3rd plus 5x squared minus x minus 6. And so first, using the fundamental theorem of algebra, we know that this degree here is 4, so we know we're looking at 4 zeros here. So looking for 4 zeros. Once we find them all, we'll have our solution. And so first thing we're going to do is try rational zeros. Okay. And to do that, we're going to make a list. Remember this rational zero theorem. This is a sub 0, or the constant. This is a sub n, or the leading coefficient. So a sub 0 is -6, and a sub n is 1. And so the factors here are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Factors here are very simple. It's just plus or minus 1. So these are the potential rational zeros. And it's just all these factors divided by these factors, but there's only one of them, so it's just plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And we don't have to manually check this, so although we can, it's a little bit tedious. Probably just use a graphing calculator here to get the job done. X to the 4th plus x to the 3rd plus 5x squared minus x minus 6. Let's start with our standard window. And you can see that it looks like there's 2 real zeros. They may even not be rational, but let's try. Let's try -1. Oh, that's one of them. Let's try +1. That's the other one. Okay? So now we have 2 real zeros here. So some of the zeros I can already answer. 1, -1. And these are the real ones. And we're going to look for, since there's 4 zeros altogether, there's going to be 2 imaginary or complex. Okay. So we're looking for 2 imaginary zeros. And so again, the way to do this, once you have a 0 and you want to find the others, just do synthetic division. So I'm going to start out with 1 here. Coefficients, x to the 4th, x to the 3rd, x squared, x to the 0. Making sure all those powers are covered. And then we can go through this relatively quickly. Bring down the 1 times 1, add 2 times 1, 2, add 7. 7 times 1, add 6, 6 times 1, 6, 0, my remainder. That's great. Do this again with negative 1 this time. Bring down the 1, 1 times negative 1, 2 plus negative 1, 1 times negative 1, 7 plus negative 1, 6 times negative 1. This is my 0. Okay. So now this is, we know that this is x squared, x, and this is the constant, or x to the 0. And well, I'm going to factor this, and just to switch it up a little bit here, I'm sorry, I should really write down my steps here. Try potential zeros, check with graph, and then use synthetic division, and then factor quadratics. So that's what I've done so far. Made a list of potential zeros, checked it with my graph, used synthetic division twice here because I have 2 zeros, and then I'm going to use factor this using whatever method is at my disposal. Just for, let's see, this is x squared, right, plus x plus 6. So I think I'm going to factor this one using completing the square, just to mix things up a little bit. Move 6 to the other side. And remember, this term that goes in here is always b over 2. This is b, right, which is 1. b over 2 squared plus b over 2 squared. And this is going to factor nicely for me. This is going to give me x plus 1/2 squared is equal, this is negative 6 plus 1/4. So it's going to give me x plus 1/2 squared equals negative 6 plus 1/4 is going to give me negative 25/4. When I take the square root of both sides, it's going to give me x plus 1/2 equals plus or minus the square root of negative 25 over 4, which is just 5 over 2i. Let me finish it over here. And then subtract 1/2 from the other side. So x equals negative 1/2 plus or minus 5 over 2i. Now I did this just mainly just for fun, but you don't really have to use completing the square. You can do this using the quadratic formula, using whatever other methods. But remember, you can't do this with graphing. It's going to have to be quadratic formula, or it's going to have to be completing the square. So the other two imaginary zeros is negative 1/2 plus 5/2 I, and negative 1/2 minus 5/2 I. And there you have it, 4 zeros. That comes from the degree, which we know these two things are connected from the fundamental theorem of algebra. 2 of them are real. We use potential rational zeros theorem to figure that out, and our graphing calculator to check. Did some synthetic division here to get it down to a quadratic, and then we factored the quadratic, or we solved the quadratic using, in this case, completing the square, but you can also have done the quadratic formula. So again, thank you for watching. Hopefully you get a big picture of things now, how everything is connected, all these little theorems and processes that we've worked on. The goal, as always, is to get a big, complicated-looking polynomial here and reduce it to its fundamental components, or all of its zeros. Okay. Have a wonderful day.